This is example 3 in the section in the lesson Emotional EMF, and is that of a loop that is a conducting loop that's entering and falling through a magnetic field. So here is our conducting loop, and it's entering this region of magnetic field at some, it's free falling into it. And the question is, and the loop has a mass of M and a resistance of R. And there's two parts of the question. Why does the loop reach a terminal velocity in its fall? And the second part is, what is that terminal velocity? So let's think about this one a little bit. So for us, the loop just enters the region of the magnetic field. The magnetic flux through it is going to be 0. And now as it's going in, we see the magnetic field is pointed into the board. So then we're going to start have an increasing amount of magnetic flux pointing into the board. And what's going to happen then is that we're going to develop a current around the loop. And using Lenz's law, that current is going to be in a direction that is going to create a magnetic field that opposes the change in the magnetic flux. So then the current is going to be such that the magnetic field is going to be pointing outwards. So then the current is going to be counterclockwise. So that's the kind of current we're going to get here around this loop. So we'll have a current of I. Now, as the loop is falling, which way does the magnetic force start acting on the loop? We're going to have magnetic force acting on any parts, any moving charges that are in the magnetic field. So we'll have this part of the loop is not going to have any magnetic force acting on it because it hasn't entered the region of the field yet. These two parts will have equal and opposite magnetic forces because the currents are going to be equal in opposite directions. And it's only on this part that we'll actually have a net magnetic force that's not going to be counterbalanced by anything right now. And the magnitude of that magnetic force, as we know, is going to be equal to the magnetic field strength times the current going through times the width or the length of this conductor, and it's going to be pointed in the vertical direction, in the K direction here. So this is the magnetic force acting now on this, actually on the entire loop, the net magnetic force acting on the entire loop. And we know that the current itself is going to be equal to B times, we'll call the motional EMF here, epsilon over R, so epsilon over resistance, W, which is the width, K. So that's, this is our magnetic force, and against that magnetic force, this is the magnetic force direction, we know that we'll have gravity, and that is just M times G. And we can now see that should these two forces become balanced, and they will, then the velocity becomes constant. That's why it actually attains a constant velocity. Why do these forces balance? Well, the stronger the emotional EMF becomes, the stronger the magnetic force becomes, and so then at some point it'll reach equilibrium with the gravitational force. So now let's find what this terminal velocity is. So this was the strength of our magnetic force acting on this portion of the conductor that's falling through the field. The force of gravity, of course, is going to be minus mg. It's going to be the minus k direction. So these two have to be equal and opposite. So then, so fb plus fg equals 0, which means that b epsilon over r w should equal to mg. Now, what is our induced EMF? It is just going to be, let me just verify here with my notes. The induced EMF is going to be B, the width of this section of conductor times the velocity. All right, so now let's put this expression for the induced EMF into here. So then we have 2 factors of b and 2 factors of w. So this becomes b squared w squared. We have 1 factor of v over r, and that equals mg. So we know the mass, we know the resistance, we know the width w, we know the magnetic field strength, we know the acceleration due to gravity, so we can just then get an expression for what the terminal velocity is going to be, and that's mgr over b squared w squared. So that's our expression for the terminal velocity, and that's the end of the solution to example 3.